All right, in this section, we are going to look at how to distinguish between linear and exponential growth. And for the support students, we looked at this a little bit yesterday, okay, but we're gonna go into more detail today. We're also gonna find future values of linear and exponential growth based upon its function. Okay, so let's start by looking at a comparison of the two. Okay, so we have two towns here. Okay, both towns have a current population of 10,000 people, but there's a little something different between both. Okay, Straight Town's population increases by 500 each year, while Power Town's population increases by 5% each year. Okay, so let's talk about how that would look in our table. Okay, so let's start with Straight Town. So Straight Town has a population increase of 500 each year. The initial population is 10,000. So that means we're starting at 10,000. So if the initial population is 10,000, then after year one, what would that population be?
10,500.
Yes, thank you. 10,500. And all we're doing, since it's increasing each year by 500, we're simply saying 10,000 plus 500, okay? After year two, we would simply add another 500 and we get 11,000, okay? And we continue. After year three, it would be 11,500. Year four, 12,000. Okay, any questions there? All right, so the type of growth here, it is growing by the same absolute amount. Okay, that absolute amount means that that's the 500 is increasing by every time. Okay, now let's look at Power Town. Power Town's population is increasing by 5% each year. Okay, it's increasing by 5%. All right, so it's still starting at 10,000, but it's increasing by 5% of the previous year. So what would it be after year one?
10,500.
Very good, that is correct. Okay, so increasing by 10,500, we would take 5% of that 10,000. So 10,000 times 5%, which is 0.05. So it means it's increasing by $500. 500 people, okay? And so we would simply add it to it. Another way that you could do it is simply say 10,000 times 1.05. And it automatically gives you the 10,500. So here, the first one, we're taking 5% of that amount, and then we have to go back and add it. But when we multiply it times the 1.05, what we're saying here is 1 plus that 5%. So it automatically adds it for us, okay? So then after 2 years, we would say 10,500 times 1.05, and we get 11,025. Okay, do it again, 1.05. Okay, and we end up with 11,576.25. We're talking about people, so we can't have a fourth of a person. Okay, so we would leave it as 11,576. Okay. After 4 years, it would be 12,155. Okay, any questions on where these numbers are coming from? Okay, so this type of growth is not going to be an absolute amount because it did not increase by the same amount every time. You see, the first one, it did increase by 500, but that's not going to be another 500 here. So we call this the growth of the same relative amount. Okay. All right, let's plot this on our graph and see what happens. So we have our x-axis and our y-axis. Our x-axis is going to represent our independent variable, which in this case is going to be the number of years. Okay, and I just simply labeled it 0 through 7. Okay, my y-axis is going to be the population. Okay, and to begin, I started with 10,000 because that was my initial population, and I counted by 500s. Okay, and so that's where you see this. All right, so if I plot, let's start with Straighttown. The initial population was 10,000, so I'm going to be right here. And then at 1 year, it was 10,500. 2 years, it was 11,000. 3 years, 11,500. 4 years, 12,000. Okay, and so you can kind of see the path that this one is going to take. I'm looking for my ruler, which I do not see what we're going to make do with this. Okay, so I connect, and you'll see just a tad. Okay. You'll see that my graph is linear. That means it creates a line. Okay. All right, Powertown, let's see what it looks like. So it begins at 0, 10,000 as well. Okay. At 1 year is 10,500. Oh, I thought this was my red pen. Here, here. Okay. And then at 2, we're at 11,025. So a little bit above our 11,000. So at 2, I would say about right here. Okay. At 3, we're at 11,576, so a little bit above 500. At 4, we're at 12,155, so a little bit above. Okay, and so it's kind of hard to see here what's going on. Because if you look, we're going to go here. Here. So we're about right there. And so what's going to end up happening is your graph is going to somewhat curve. Okay. Now, we started our y-axis at 10,000 and went to 13,000, counting by 500s, okay? But if we adjust our x and our y-axis, okay, adjust our x-axis out to 50 years, adjust that population further up, and instead of counting by 500s, we're counting by 10,000s. So we've increased the range of our x and our y-axis. You get a better picture of how the graph is looking, okay? So this is Straight Town, which is still linear, but if you look at Power Town, you'll see between that 0 and 10 years, which we plotted initially, which was here, okay, between that 0 and 10 years, which was here, it's kind of hard to see the change, okay? But if you notice, right before 15 years is when we have what we call the first doubling, okay? And at that first doubling, then you can see more prominently what's happening to your graph, okay? So Straight Town is what we call linear growth, and it's linear growth because it's growing by that same absolute amount each time. And with Straight Town, we had already figured out that that absolute amount was 500. Okay, so anytime we increase or decrease by the same amount every time, we call that linear growth, and it will create a line. Exponential growth occurs when a quantity grows by the same relative amount, okay? Relative amount means the same percentage in each unit of time, okay? And so with Power Town, remember, it wasn't increasing by 500 every time, it was increasing by 5%. And because it is a percentage, that's what we mean by relative amount. And exponential growth creates what we call a J curve, okay? That means this kind of looks like the letter J, okay? Questions here? Okay, all right, let's look at some examples. All right, so let's determine if the situation is linear or exponential, and then we're going to answer any additional questions. So example 1. Tony makes a yearly salary of $32,000. His company increases salaries yearly to allow for COLA, which is the same as cost of living adjustment. Okay, and this increase is of 3%. Says, what will Tony's salary be in year 1 and year 2? And round your answer to the nearest dollar. So the first thing that we need to do is determine if it's linear or exponential. And we determine if it's linear or exponential by how it is increasing or decreasing. And so if we look here, it tells us that the company increases the salaries by 3%. So because that increase is a percent, this is going to be exponential growth. Okay. Now, there was something that I neglected to go over with you. So let's take a step back. So here, when we talked about linear and exponential growth, your form for linear growth is going to be y is equal to mx plus b, okay? And support students, we talked about this a little bit yesterday. your form for exponential growth is going to be y is equal to a times b to the x power. So if it's linear growth, when we write it out in terms of an equation, in terms of its function, it's going to look like this. And if it's exponential growth, it will be in this form, okay? All right, so now let's go back. So we know that this is exponential growth. So in year one, if he started at 32,000, then with the cost of living adjustment of 3%, he's going to be what at year one? So we would take 32,000 and multiply it times that 1.03, okay? Because that's the 3% increase. And so at year one, his salary will be $32,960. Okay, his salary in 2 years, year two. We start with where he was, okay? Because now he's at 32,960 and we multiply that times that 1.03. And we end up with $33,948.80. And we're gonna round that to 49. So he would be at $32,949. Okay, questions on where these numbers are coming from?
And that 33,000 in year two?
It is, thank you. Thank you so much, 33. Yes, I just wrote that down wrong, yes, okay. All right, so let's talk about what the actual function would look like. So we know that it's going to be exponential. And so we would be looking at y is equal to a times b to the x power, okay? A represents our initial amount. So the yearly salary that he started off with was 32,000. So we would say y is equal to 32,000, okay, times b is our growth factor. And so it was increasing by 3%. So we would say 1.03 and then put it to the x power. So this function allows us to figure out what his salary would be at any given year, with x representing your year. Okay, questions there? Okay. All right, number 2. A certain vehicle was purchased for the price of $24,950 and decreases in value by $900 a year. Says what will be the value of the vehicle in 3 years? Okay. So first of all, we want to determine if this is exponential or linear. So we need to think about how it's increasing or decreasing. Is it increasing or decreasing by a percentage or by an absolute amount?
It's decreasing by an absolute amount.
Very good. Yes. It's decreasing by $900 every year. So we call this linear because it's an absolute amount, but it's going to be decay because it is a decrease. Okay. All right, so let's think about what this function will look like. So remember we said the linear function is y equals mx plus b. But in this case, it's decreasing. So that would be y equals mx minus B. Okay. B is my initial amount. So my function is going to be y is equal to negative, and I'm sorry, that was my fault. We're gonna do it this way, Lord. This should be y is equal to negative mx plus b, because it is a decrease in the absolute amount, okay? I was incorrect here because this is my initial amount. So the initial amount should not be changing. Because it's a decrease, my slope or my rate of change will be negative as opposed to positive, okay? All right, so let's go back here. So if we are decreasing by $900 per year, this is going to be negative 900x plus my initial amount, which is 24,950. So this is my function. We could also write this as y equals 24,950 minus 900x. These are the same. Okay. Questions on where the function is coming from?
Is there a way to do it for the 3 years in the?
Yes, so what we're going to do now, this is the function. And so what we can do now is when it's asking what will the value be in 3 years, this x just simply becomes 3. Okay. And so we'll say y is equal to 24,950 minus 900 times 3. Okay, so 24,950 minus 900 times 3, and we get 22,250. And this represents the depreciation value in 3 years. Okay. This function, by creating the function, it just makes it easier for you to determine the amount based upon the year. Okay, I know 3 years is, it's pretty simple. All you had to do was really say 24,950 minus 900 3 times. But what if it said 15 years? So instead of having to just keep going minus 900, you can just put it into your function. Okay. Questions? Okay, let's look at a few more examples. All right, so the next one. The number of students at Wilson High School has increased by 50 in each of the past 4 years. If the student population was 750 4 years ago, what is it today? So first of all, linear or exponential growth or decay? Okay, let's think about how it's increasing or decreasing. So first of all, we see increase. So that tells us it's going to be growth. It says it's increasing by 50. Okay, that's not a percent. So because it is an absolute number, that tells us we are going to have linear growth. If it was a percentage, then it would be exponential. Okay. So our function would be y equals, anyone want to take a stab at it? What's our initial population? 750. So that's our starting point. Increase, so plus 50x. So again, when we're talking about linear, we have our initial or our starting point plus or minus whatever that change is, okay? And then the question is, if the population was 754 years ago, what is it today? So that means our X is going to be 4. So we would say Y is equal to 750 plus 50 times 4. And so our answer is 950. Okay. Questions? Okay. All right, I want you to take a minute and try B. All right, what did y'all come up with? Is it linear or exponential, growth or decay?
Exponential growth.
Very good. So we have a rising, so that tells us it's going to be growth. And it is a percent, so that tells us it's exponential. So exponential growth. Okay, so let's think about how this function is going to look. So Y is equal to, what's our initial amount? The price of the milk was $4 a year ago. So that's our initial amount. So 4 times our percent is 3. So that's going to be 1.03 to the X power. And I just put parentheses to represent my multiplication. Okay. Any questions on where the function is coming from? All right. So the question is, if the price was $4 a year ago, what is it now? So that means my year, my X is 1. So I simply say Y equals 4 times 1.03 to the first power. Okay. And if I put that in my calculator, you should get $4.12. Okay. Questions on B? All right, last example. Tax law allows you to depreciate the value of your equipment by $200 per year. If you purchased the equipment 3 years ago for $1,000, what is the depreciated value today? Okay, so first of all, is it linear or exponential, growth or decay? So depreciate means that it's decreasing. Okay, so that's going to be decay. And then it is decreasing by $200 per year. So that is an absolute amount. So this is going to be linear decay. Okay. Our function is going to still begin with Y equals our starting amount. It was $1,000 3 years ago. So that's our starting amount. And then remember, it's decreasing. So that means it's going to be minus, and it's decreasing by $200 a year. So 1,000 minus 200x. And this is my function. Any questions here? Okay. The question is, if you purchased the equipment 3 years ago, what is the depreciated value today? Anyone get that?
Is it 400?
It is, very good. So y is equal to 1,000 minus 200, my x is 3. So 1,000 minus 600 is $400. Okay. All right, questions, guys.